sleepy or you still there? Okay, that's good. So I would I like to try to do a very hard task, so to speak about the ionosphere in 1 hour. So it's a very, very hard task. So but first of all, I would like to thank Claudio, Lucilla, Yuri, Professor Sandra Dicella, who some of these slides are being stolen by them, from them. And then part of them have been inspired by the lesson given by Professor Michael Mendillo in a school we had some years ago. So I'd like to start with some kind of history. So everything began with the electromagnetic theory of James Clerk Maxwell. And in 1899, Guglielmo Marconi invented the first radiotelegraph, sending signals across the English Channel. Then everything changed in 1901 because there was a transatlantic radio signal transmitted from Cornwall to Newfoundland in Canada, and it was the first transmission using the ionosphere as a medium to transmit the signal. And for that, Marconi was awarded with a Nobel Prize in a few years after, sorry. Of course, we didn't talk at that time, they didn't talk about ionosphere. The term ionosphere arrived slightly later. The theory of an atmospheric layer of ionized air called the Kennelly-Heaviside layer was theorized by them a few years after. Now we call that ionosphere. And then the existence of the ionospheric layer has not been proved until the 1924, thanks to research of Edward Appleton. Okay? So this is a little bit of framework of the history of ionosphere. But today I would like to bring you into this journey to build the ionosphere. So first of all, we have to know what we have to cook together. So what's the ionosphere? The ionosphere is a plasma, good news, but it's not a very peculiar plasma because it's a plasma able to influence the propagation of radio waves from kilohertz to gigahertz range. It's globally neutral. The density of ion electron is very low with respect to the neutral density. It's a cold plasma, so it means that the collision energy can be neglected in most of the cases. It has its own plasma frequency, and this plasma frequency depends on the density of the free electron characterizing that plasma, and they have a big variation in terms of space and time. And there are relative maxima and minima of electron density that identify the various ionospheric regions or layer. The ionosphere somehow, as you may see from this figure, is the ionized counterpart of the thermosphere, covering a range between roughly 50 kilometers up to 1,000 and more. Okay, that's what we have to cook. So, a good recipe for the Earth ionosphere, this is the doses for one planet. So you have to sprinkle a generous amount of photoionization. You need plasma, so you need photoionization. So photoionization is the process. You have some molecules, some atoms. You need photons with a given energy. So H is the Planck constant, and nu is the frequency of that of the photons. And if the energy has exactly the quantum needed for the photoionization, you create an excited version of the atoms plus an electron. So you extract an electron from that. So somehow, if you want to photoionize a part of the atmosphere, you need the two ingredients. The first ingredients are the neutral. So you need to know the composition of the neutral atmosphere. Here you may see a good approximation. So the most abundant species in the atmosphere are the oxygen and the nitrogen, the molecular hydrogen, with other good composition made by hydrogen, molecular oxygen, and helium. This is somehow reflect the fact that heaviest species are going to lower altitude. This is because of the gravity. And then you need some photons, good photons, and there is the sun, luckily. So, of course, you need photons that have exactly the energy you need to make the electron pass from one orbital to the other. And here you can see the energy needed, that is a specific quantum of energy here reported, also in terms of the specific wavelength that that photon must have to enable the photoionization. Okay, that's good. So let's imagine, let's put ourselves in a simple case. So we have just an atmosphere made by oxygen. So we need a photon with a wavelength of 910 angstrom to produce an ionized an O plus an electron. So in the Chapman theory, I will going to tell more about that in a few slides, the production function is the sum of the distribution of the concentration of oxygen with the altitude and the radiance as a function of the capacity of the solar radiation to penetrate in the various layers in the atmosphere. So, how do you imagine? What shape do you imagine for this? It's not that hard to imagine, because if you think about the concentration of neutrals, so they go up, they go down with the altitude, okay? And what do you imagine for the radiance as a function of altitude? It goes like this, because the photons tend to be absorbed by the various layers of the atmosphere going down, and then you can imagine a distribution of the solar irradiance as a function of altitude, which has this form. So if you want to convolve these two functions, you get this. That is a beautiful ionospheric layer. That's a beautiful, very simple model, with a single species inside, ionospheric layer. What you can do actually is to try to make something a little bit complicated, but the theory is always the same. So if you imagine a single composition, you can obtain what is called the Chapman layer, and you see there the expression of the electron density as a function of the altitude, as a function of the height. And here you can see some important factors. Of course, you need to take into account the rate of photoionization and the solar zenith angle, which is somehow, it's the angle, gives you the idea that how the sun is efficient in transferring photons from the sun to the atmosphere. And I deleted that part, which is called recombination rate, because we are going to talk about recombination in a while. But at the beginning, you can think that you have something that depends on the neutral density, it depends on the irradiance, and somehow also dependence on the solar zenith angle. This is the most simple ionospheric layer you may think of. Let's start to complicate a little bit more the things. So you need also to take into account that there is a cross-section, of course, so the efficiency of the photons to really actually create ionization in the plasma. And if you have a photon characterized by a wavelength which is larger than the one needed for the ionization, there is no photoionization. Of course, if it's smaller, you will have the photoionization, plus some extra energy. So in theory, you may have an energetic photoelectron with a specific kinetic energy. You can call it E star. So if this extra energy is again larger than ionization potential, you can create a secondary ionization. So a very energetic photon can lead to several ion-electron pairs. So you can have just primary and secondary ionizations. And this is again just in the case of a single species. So if we want to take into account and we want to consider a complete photoionization, we have to take into account the full irradiance from the sun, and the full density of the various species as a function of the composition of the neutral atmosphere. If you remember, this is on the left, you will see the solar flux on the various wavelength and frequencies, and also here reported for two different levels of the solar activity, so the solar maximum and solar minimum. And the other side, I have reported here again the composition of the neutral atmosphere. If you remember the table I showed you before about the wavelength needed for the photoionization, you will see that the range of wavelength creating the ionization of the species in the upper layers of the ionosphere are in the range between the X-ray and the UV ray. Okay, and these are, again, I've reported the main sources of the primary ionization in the ionosphere. Okay, that's the first ingredient. What's the second ingredient? We have to add an almost uniform dusting of particle precipitation around the magnetic poles. So besides the solar irradiance, there is another source of ionization. The fact that, as both Stefan and Fabien already demonstrated you, the Earth system is not closed. See, the Earth ionosphere, in terms of currents, is exposed to magnetosphere. It's directly connected the ionosphere to the magnetosphere and the solar wind. So it's open, especially under specific conditions, to the penetration of particles that create currents and the particles are precipitating at lower altitude and may reach ionospheric altitude. In particular, if you see this plot, precipitating electrons, this is the distribution of a function altitude of the ionization rate for different energies of the precipitating electron, can create an additional source of ionization affecting mostly the zone that you have seen before, so the zone characterizing the auroral oval, so the auroral precipitation oval. Okay, so photoionization is the first ingredient. Particle precipitation is an additional source. What's missing? We had to add a wise dose of chemistry. Why? Why a wise dose of chemistry? Because we put too much ionization in our receipt. Why? If we consider just the production, and we consider, for instance, the case of the oxygen, and this is a model of the production rate by considering just photoionization of the oxygen, we may consider that at the peak ionization rate we have kind of 4,000 electrons per cubic centimeter per second. So if we wait 3 hours, for instance, so about 10 to the 4th seconds, we have a maximum density of 4 times 10 to the 7 electron per cubic centimeter. That has been never measured. It's really too high. So something happened. So some electrons must be somehow, something happens to these ions and electrons. And the answer is the chemistry. So the plasma recombination and some neutral plasma processes must be taken into account to complete the picture. What I mean is that, for instance, we can have electronic capture, so some excited oxygen can capture an electron and create, and going back to the atomic state. This is very rare because you need exactly an electron which have very peculiar energy. So then it's a peculiar wavelength, so the 910 angstrom I was mentioning before. Another case can be the capture of electron by molecular ions of oxygen. This is fast, it's quite a fast process. Or we can have the process involving the excited oxygen plus molecules of nitrogen and oxygen, creating excited states of okay, I don't remember the name, NO plus, that can further decay, that transform into oxygen and electrons in excited states. And it's a slow process. And of course, when there are processes that are characterized by this two-stage process, they are slower. The effect, the net effect, is that the recombination plays an important role. It can be so slow that makes the ionosphere existing also during the nighttime, so where the main source of its creation is not there anymore. And of course, the ratio, for instance, of the oxygen and N2 it's an essential quantity that provides some knowledge about the ionospheric state, because the density of the oxygen affects the production rate in the F region, and the lifetime of the oxygen at F region is governed by this dissociative recombination with N2. So somehow, if you want to know about the chemistry that is going on, that is changing the status of your ionization, you have to monitor, you have to keep track of the ratio between the oxygen and the molecular nitrogen. So again, the same plot. I have reported there the main source of recombination. And of course, the real case, it's more complex. So many chemical reactions happening in the ionosphere, and a more complex picture. In the actual case, it's almost like that. So on the left part, you will see the various sources of the various ionized species in the ionosphere. On the right, you will see the density of the neutral one, which, as you may see, they are more dense than the excited counterparts. And the electron density distribution, which is the black profile you will see there, it's mainly driven by the electron density distribution of the ionized oxygen. And when you have the peak at around 300 kilometers, it's the O plus that is dominant. At lower altitudes, going below 150 kilometers, the major ions are O plus, O2 plus, and NO plus. And at higher latitude, it's the lighter elements that dominate, specifically the hydrogen, the excited hydrogen, which mark the transition towards the protosphere and plasmasphere. So the most clear, the most striking feature of this combination of various species is that the ionosphere, the plasma, has a structuring, it's vertical structuring. And in particular, you may recognize here in blue and red the various layers that compose the ionosphere. On the right, in red, there you have the typical daytime ionosphere, which is composed by 4 layers, D layer, E layer, F1, and F2. And a less structured ionosphere is during the nighttime with just the E layer and F layer. And here you also see something that you will see many times during these days, the fact that there is a GNSS satellite there, which has some signal that passes through the whole ionosphere and keep memory of many things. But the most important part is the total electron content, which is the integral of the electron density along the ray path connecting the GNSS satellite and the receiver. You will learn a lot about instrument, you will learn a lot about EC in the next day, so start to be familiar with that. Okay, let's say a few words about the ionospheric layer. So The D layer is located at about 60 to 90 kilometers. The production mechanism is mainly the daytime ionization of NO due to solar Lyman alpha at that specific wavelength. The loss is due to recombination with complex ions. It has the characteristics to absorb the lower radio frequency, so some instruments are not able, for instance, radar located at ground that are called ionosphere, are not able to reveal the D layer of the ionosphere and disappear right after sunset because there the density is such that their combination is completely able to make the layer disappear. Then there is the E layer from about 90 to 140, 150 kilometers. The production mechanism is the daytime ionization of O2 and the particle precipitation in the high latitude sector. If you remember, the penetration of the particle precipitation was at about, at a maximum at about 150 kilometers. And the loss is through the recombination with modular ions, and it's also ruled by the by molecular ions, and it's strongly driven by the solar zenith angle, as I mentioned in the Chapman layer. In fact, it actually behaves quite nicely as a Chapman layer. The F1 layer is from about 140 and 200 kilometers. Please don't take this number as very strict. It's just rough. They change a lot. And the production is the daytime ionization of oxygen, and the loss is recombination of NO plus and electrons. And okay, it tends also to behave like a Chapman layer. And the F2 layer, which goes up to the 1,000 kilometers and more, and has a peak typically at about 300, 350 kilometers. As I mentioned before, the daytime ionization of oxygen is the main production. The loss is the O plus reaction with N2 and recombination of NO plus and electrons. And it is also significantly affected by transport and diffusion processes, which make the F layer deviates from the ideal behavior of Chapman layer. Okay. Now we need to season it all with a strong internal magnetic field, because the magnetic field has an important role in the ionosphere formation, morphology, and dynamics. We know now, also even before, that the Earth has a magnetic field. The magnetic field is nearly vertical at the poles, and it's nearly horizontal at the equator. And it plays a significant role, especially at mid-latitude, for what concerns the fact that the neutral winds are mostly horizontal, and the plasma is constrained to move along the magnetic field line. So if you see this simple calculation in which you take into account the inclination of the field and how this converts into movement of the plasma, you may see this dependence on the velocity on the vertical component, dependent on the cosine and sine of the inclination angle. So this effect is maximum at the equatorial, at the mid-latitude, and it's small at the equatorial and high latitudes. Of course, if we neglect the fact that neutral wind may create polarization fields that can alter this picture, but the morphology of the magnetic field creates very important features at high and low latitudes. So the dynamic of the plasma is ruled out by the E cross B drift. So the velocity of plasma depends on the vectorial product between the electric field and the magnetic field. And at high latitude, you remember that the magnetic field is nearly vertical, okay? If you remember the field line current I mentioned before, they create electric field which is horizontal. And in particular, you may see here the convection cells that are responsible for the electric fields in the high latitude ionosphere. You may see 8 configuration of these convection cells depending on the relative balance between the Y and Z component of the interplanetary magnetic field. So this creates a movement of plasma across the convection shells, which is called the tongue of ionization, which is especially intensified during the geomagnetic storm. So when you have entrance of particles from the outer space, from the magnetosphere down to ionospheric altitudes. So you have mainly particles enters in the day-side sector, and they start to migrate, cutting into the polar cap and create this large-scale structure of the ionosphere that you will see again when we will talk about irregularities, which is called the tongue of ionization. So, and for instance, it's very important because it creates gradients of density, which is the main trigger of some instabilities, like for instance the Kelvin-Helmholtz instabilities you have heard about from Stefan before. The situation at low latitudes is different. The magnetic field is horizontal and the electric field now it's directed to the east-west direction. It is mainly created by the neutral winds that act in this way. You will see here the latitude as a function of the magnetic local time, so it's a local kind of local time. And it creates this current system. The current system which is called equatorial electrojet. So the net effect is that the equatorial electric field is directed into the east-west direction. The B is horizontal, so the net effect is to have a velocity of the plasma which is in the up-down direction. In particular, it pushes the plasma up. And it creates this specific feature of the equatorial ionosphere, which is called the equatorial ionization anomaly. So in absence of the magnetic field, you would have expected that the photoionization create a maximum exactly at the equator. It's like in the normal weather, I will say. In this case, there is a pushing up of the ionospheric plasma that tends to get down off the magnetic field line, create these 2 peaks of ionization, which are called the crest of the equatorial anomaly. And you may see here a model simulation of the ionospheric density as a function of the altitude, in this reported in this nice review paper by Nandan Balan, published 5 years and a half ago. And you will see this excess of plasma located around 15-20 degrees off the magnetic equator. And this creates one of the largest ionospheric structure you may see. And this is actually this beautiful picture in which the 2 crests of the equatorial anomaly are nicely depicted. That's the full story for low latitude ionosphere? No, far from being true, because what do you expect? When the sun is disappearing over the horizon, the equatorial ionization anomaly should disappear somehow. Yes, but these are the most unstable situation for the ionosphere, because when you have the passage of the solar terminator, there are also changes in the electrodynamics. In particular, there is a weakening of the E layer in the conductivity of the E layer and increase of the F layer conductivity. And this creates an uplift of the F layer. And the uplift of the F layer with respect to E layer create a bottom side gradient. It creates bubbles that tends to go up and then descend along the magnetic field line, creating a so-called array Taylor instability. And these are the most disrupting effects for trans-ionospheric or radio waves passing using the ionospheric layer for bouncing. These are called the equatorial plasma bubble. You will see here a snapshot at different times of the simulation of the plasma bubble evolution, which tend to be, there are plasma depletion that tends to grow, and then they start to grow also and to decay along the magnetic field line and create this small-scale structure you will find later in my presentation and in the presentation about ionospheric irregularities I will give on Wednesday. These are, again, among the largest ionospheric structures. They can stretch up to 500, 600 kilometers in altitude, and they extend for a big band of latitude, as you may see in these nice plots from the, on the left. In plasma bubble are exactly these, you may see these holes that are here, which are exactly the bubbles going up and decaying along the magnetic field line and covering a quite huge band. You will see that they are a very regular, but not completely regular phenomenon occurring between, at the equinoxes, mostly at the equinoxes under solar flux condition, and are really a big trouble for GNSS-based positioning, for instance. Okay, we have almost finished the recipe. We have to steer everything to achieve the regular variation. So the most important regular variation you already seen is the day-night variation. You may see here another way of thinking this. This is the mean daily variation of the total electron content above Italy. So it's mid-latitude, but it's sorted into low, mid, and high latitudes, Italian latitudes, okay? So it's not low latitude, that's Sicily, Rome, and Alps, I would say. And as you may see, Italy, it's about +1 with respect to UT. So you may see here that you have a peak of ionization during the daytime, which tend to decrease in the night. I mean, it's minimum around midnight, around midnight. And you have also a slight dependence on the latitude. So the lower the latitude, the higher the ionization. Okay. So at mid-latitude, as with the normal weather, less solar radiation translates to less photoionization. This is quite true, for instance, for the E-layer behavior. The peak density during daytime, for instance, is lower in winter rather than in summer. But it's not completely true for the F layer, because you may remember that the dynamics of the morphology, the dynamics and the formation of the F2 layer is significantly influenced not only by the photoionization but also to the transport processes I have mentioned before. So you start experiencing, while you consider the F layer, to some anomalies. I don't have time to go into the detail of these anomalies of the ionospheric behavior, which are called the winter anomaly, the annual anomaly, and the semi-annual anomaly, but I have put some slides for you. You will get access. Just in brief, I would like to mention that the winter anomaly is that you have a greater F2 layer peak density in the winter hemisphere than in the summer hemisphere during the solstices. In the annual anomalies, that you have a greater F2 layer peak density at global level during December solstice than June solstice. And the semi-annual anomaly is that the F2 layer peak density is greater at the equinox than at the solstice. Another important part is that you know that the sun has a cycle, half of a cycle, it's 11 years, and you may spot this variability by monitoring the sunspot numbers or the F10.7, which is the flux at that specific wavelength, 10.7 centimeter. It behaves like this, so it's the way you can recognize and spot minimum, minima, maxima, and ascending and descending phase. So, what's the dependence on the ionospheric behavior on solar cycle? This is the paper published a couple of years ago, investigating the total electron content over a GNSS receiver located in low latitude. This is Africa, in Gabon, called Tang. And that's in blue, and in red you will see a sunspot number. You will see that the behavior of TC nicely follow the behavior of the sunspot number. You will see also, you can also nicely draw a linear fit between the two. But this is true not only for a specific place on the Earth. If you consider what we call the global electron content, the global electron content is a measure of the total electron content at worldwide level, and this is reported as a function of the solar flux at 10.7 centimeter. So there is a nice agreement between the solar activity and the TC and the electron density in general. And we have to shake the ionosphere. So we have to shake with some irregular variation, because they are the most somehow intriguing. If there were no irregular variation, we would probably not be here all together to talk about these things. So you start realizing today, maybe you already know, that the near Earth space is a very complex environment. There are many processes. You can think in terms of exchange of mass and energy. You can think in terms of a change and changes and variation in currents. From whatever point of view, it's a mess. And this is probably the most famous, one of the most famous figures you may see when relating with this field, illustrating all the processes. Of course, every of these arrows will deserve a series of lessons. So this is just to give an idea, a brief idea at a glance of the complexity of the situation. But the ionosphere is peculiar not only because it's exposed to the geospace forcing, but it also exposed to forcing from below, from the lower layers of the atmosphere, through the so-called lithosphere-atmosphere ionosphere coupling, which is becoming more and more important in the recent years. Okay, if we want to simplify the problem, we may say that there are three main sources of geospace forcing to the ionosphere: solar flares, so neutral radiation suddenly impacting the ionosphere up to until roughly 8 minutes after they are launched from the Earth. They are neutral, so they directly affect the ionosphere. There is no the magnetic field doesn't matter for them, though the interplanetary magnetic field doesn't matter. And then there is the exchange of particle and energy through the coronal mass ejection and the high-speed streams that affect the ionosphere through the coupling with solar wind and magnetosphere. And they have different response time. So it's about 1 to 3 days for coronal mass ejection. It can be tens of minutes to a few hours for the fast proton and alpha particle constituting the high-speed streams, for instance. So again, this provides another proof of the complexity, because also from the timing point of view, there are delays that must be taken into account. So I was talking with, I don't remember, with you before. You're interested in flares, no? Am I right? No, you, sorry. So, what's the impact of the flares of the ionosphere? They are very fast. They create extra ionization, increasing the density mainly of the D layer. So they create a denser and thicker ionospheric D layer that absorbs everything, almost everything. You will see here, this is an example of a flare occurred. This is the strongest flare in the recent past, the X9.3 flare occurring during the September 2017 storm. The subsolar point was located near to the UTC 12. And it creates an absorption until 35 dBs. This is the highest frequency affected by 1 dB absorption, so it almost blinded all the frequencies in the HF range. And you can see there also the ROTI. It's a quantity derived from GNSS. It's the time. It's related with the time derivative of TC. So it demonstrates how fast the TC in the ionosphere change. And you may easily recognize that there is a kind of bomb impacting the ionosphere. You will learn about these techniques also from a talk from Tobias tomorrow. Tobias, am I right? Okay. So this is, it's not that clear, but if you use HF radar called ionosonde, you may reconstruct the bottom side of the ionosphere up to the peak layer, and on the top plot you will see a typical ionogram. It's a good ionogram from an ionosonde located in Rome, and this is exactly the same ionogram during the flare. What you can see below is not matter of the figure. It's not matter of the projector, nothing, because everything is absorbed. Every frequency emitted by the ionosonde is absorbed by the ionosphere, so you can't see any echo from the ionosphere. You may also see jumps. I will put you a slide for you. I don't have time to speak about, but you can also see clear jumps and fast jumps in total electron content. Let's go to the charged part of the problem. So CME and high-speed streams. So when you have geoeffective storms, you have jumps in your, you have flips in your Z component of the IMF. You have increase of flow speed and dynamic pressure, and you can start to interact and influence the ionosphere, starting from the coronal mass ejection in high-speed streams. So when a CME or a fast solar wind streams hit the Earth, the whole system reacts through the solar wind magnetosphere ionosphere system, and there are a plethora of effects affecting the Earth. You will have enhanced particle precipitation at auroral latitude. You have modification of the ionospheric current at high and low latitudes. You have modification of the neutral composition. You have heating of the ionosphere. You have displacement of the boundary of the auroral oval. There are wave-like disturbances. You will learn a lot in these days about traveling ionospheric disturbances. You have changes in the polar cap circulation. You have a plethora of events. Here there is an example. Again, this is the ROTI, the quantity I've mentioned before, so the variation of TC. During the June 2015 storm, again, one of the largest of the La Paz solar cycle, and you will see here, there's no need to go into the details of what you see here, but you see there are many different phenomena affecting different parts of the ionosphere. You have to imagine this as a map, as a flat ionosphere at 350 kilometers, okay? Because the GNSS is not able to resolve the height. So you see activity on the high latitude, low latitudes, mid latitudes, really a plethora of events. The most intriguing part of the geomagnetic storm, the solar storm, which translates into geomagnetic storm, which translates into ionospheric storm, is the formation of ionospheric irregularities. I will speak about that on Wednesday. In general, you may note today that our plasma density variation with a general background smooth ionosphere, and they are created during, but not only, during geomagnetic storm, and they are or created or modulated, and are very important because the underlying phenomena affects a lot of application like GNSS positioning, HF communication. And the most important thing is that they range on a very large scale. They are featured by a large scale size range from centimeter up to 1,000 kilometers. 1,000 kilometers, okay? And you can see here again the plasma bubble, what they are called the storm-enhanced densities that affect mid-latitude, the tongue of ionization, and the crests. So, what happened in the high-latitude ionosphere? So, mostly you have increased ionization to particle precipitation. On the left, you have the case of the electron density changes induced by the 2003 Halloween storm. On the right, you have a model which depicts the electron density variation during the 2015 St. Patrick's Day storm. And I think that those animations speak for themselves, because you see there are increase of ionization, increase of particle precipitation, and waves that start to affect the rest of the ionosphere. The peak here has already passed. These are probably the most studied storms of the past, together with the September 2017 storm. Again, for what concerns the response of the high latitude ionosphere, there are changes in the shape and convection cells. These create different features related to the tongue of ionization, so how it is created and how the plasma tend to move across the polar cap, and also tend to fragmentate because there are also instability processes occurring while the tongue of ionization grow and moves across the polar cap. And of course there is also a displacement of the auroral oval. These are the examples of two storms. So again, the 2015 St. Patrick's Day storm and 2002 storm, and this is the Halloween storm, this one, depicting various stages of this storm, again in terms of this Rothe index, that are here just to demonstrate the highly dynamic environment, especially at high latitude, you may experience if you want to study the formation of irregularity is as a response to the geospace forcing. What happened to low latitude? The most important part of the low latitude is the fact that the low latitude ionosphere is mostly ruled out by the electrodynamics, and the occurrence of a geomagnetic storm alters the electrodynamics of the low latitude ionosphere. So this is the solar quiet conditions. This is the solar quiet condition in creating the equatorial electrojet I've mentioned before. When there is a flip of the BZ component of the interplanetary magnetic field, there is a specific phenomenon called prompt penetration of electric field. The field and line current I mentioned before, the inner part are connected with the magnetosphere. The field and line current or region 2, which are the one at lower latitudes, are connected with the ring current. And they react with different times to the geospace forcing. So the one connected with the magnetosphere tends to react first, creating an imbalance by these two current systems. And then the region 2 field and line current tends to balance this initial balance. This creates some undershielding conditions that allows penetration of electric field from the magnetosphere down to the ionosphere through the ionospheric waveguide. And then this is at the flip, the southward flip of the magnetic field. So when BZ turns to negative values, and the opposite happens in the opposite condition. And this penetration of electric field is a prompt response. It is a shorter duration, and it affects the electrodynamics from about 30 minutes to 2 hours. Then the ionosphere at high latitude start to heat up because there is particle precipitation that creates particle heating, Joule heating, so winds start to move, as you may see here, so traveling ionospheric disturbances. They start to move, trans-equatorial wind starts to move and affect the electrodynamics of the low-latitude ionosphere, create a delayed effect, which is called the disturbance dynamo electric field. So the resulting effect is an interplay between these two, with this prompt and delayed effect. And the most important thing is that it has a strong dependence on the longitudinal sector, on the local time dependence on the storm, of the storm development. This is a very nice example from a paper by Bruno Nava and other colleagues. These are three geographical sectors, three longitudinal sectors: Asian sector, African sector, American sector, and this is the TC as a function of time and latitude for those three sectors. You may recognize before the storm, so here, quite nicely the signature of the crests of the equatorial anomaly. Okay, you may see it. When the storm commences, you have strongly displacement and strong changes and strong displacement of the crest of the equatorial anomalies, asymmetries, which are dependent on the longitudinal sector you are investigating. In particular, see in the Asian sector, at the storm peak, the crest signature completely disappear. And this also has an important effects also on the formation of plasma bubbles. Right? So these are one of the most challenging things to model in the occurrence of irregularities in the low latitude sector, and there are still many efforts in place to understand how the storm time behavior affect the formation of the irregularity and also of the crest when geospace forcing is pushing. What about mid-latitude ionosphere? The most striking effect of the mid-latitude is the so-called positive and negative phases of ionospheric storm. You may see here again two examples taken from ionospheric measurements over Italy. Here on the top plot you have total electron content over Italy, and below you have the critical frequency of the F2 layer, which is directly proportional to the to the frequency of the F2 layer, again over Rome. In red, you have the median behavior, obtained by considering the 27 days before the specific measurement, and in green you have the behavior. You may recognize that the first day here is March 2022. There was a storm starting on 23. There is a good agreement between the actual behavior and the median behavior, while there are negative and positive variation when the storm starts. In particular, you have a positive phase, and before, so there is an extra ionization with respect to the median behavior, and then there are lesser ionization with respect to the median value in the second part of the storm. And this is quite a regular response of the mid-latitude ionosphere to geomagnetic storm. In particular, here in this behavior, the variation in the neutral composition plays a significant role. You may see here there is the density of the neutral recorded by the use of the swarm satellites. And you may see here this is from 22 to 25, exactly the same time range. I don't know why the dates are disappeared there with the KP index. So you may see the small increase in the neutral density experienced recorded by the satellites. And you may see here in this it's a masterpiece of Professor Michael Mendillo about TC behavior. You may also recognize different feature and different patterns of the negative and positive phase of the swarm. It's a very complex scenario, but most of them is ruled out by the changes in the neutral composition. What else about storm time behavior? So you will learn about traveling ionospheric disturbances. I was mentioned before the precipitation of particles eats up the ionosphere in the high latitude sector. This create winds, as you may see there in this modeling during the St. Patrick 2015 storm, that tends to migrate to lower latitude and alter the plasma density by consequence. On the left, you will see the DTEC. So you may recognize, if you want to recognize waves-like structure in your total electron content data, you have to detrend to highlight the oscillation, and you easily and nicely recognize this wave-like structure, for instance, here passing over the Europe, but also over the American sector, that are actually the traveling ionospheric disturbances. There will be plenty of lectures dedicated to that in the next days. Besides large-scale traveling ionospheric disturbances, there are also medium-scale traveling ionospheric disturbances, and they are mostly the TIDs in general, the most important ionospheric effect at mid-latitude, threatening application like positioning and HF communication. They are characterized by the different period, wavelength, and also typical variation with respect to the background ionosphere that carried out. And the interesting thing is that the traveling ionospheric disturbances are created by a plethora of phenomena, especially the medium-scale TID. And you can see on the left an example of medium-scale TID created by the rocket launch, so the Falcon 9 rocket launch. This is the case of, probably you heard about it, the Unga Tonga Pai explosion, which is becoming kind of what was the Halloween storm. It's a standard candle for the lithosphere, ionosphere, atmosphere coupling. And here you can see the passage of the wave over Japan. But there are also nuclear explosion, volcanic explosion, hurricanes, tornadoes, thunderstorms that creates mass TID and are worth to be investigated, because TIDs are silent accuracy killer, because a GNSS receiver doesn't know if a TID is passing over his head, for instance. Okay, I'm going to conclude. So, some take-home messages. The ionosphere is the upper atmosphere region containing a large concentration of electron ions due to the ionization of the outer atmosphere gases by solar ultraviolet and X-rays. It's structured, it's vertically structured, it is composed by layer, and it's formed by an interplay between ionization, production, loss, and transportation processes. The presence of the magnetic field is a fact, and it's important to understand the morphology and dynamics of the ionospheric plasma. It has variation with altitude, local time, season, and solar activity level, which are usually referred to regular variation. As the ionospheric plasma has an impact on sub- and trans-ionospheric radio signal propagation, it's important to study ionosphere for many applications. Usually ionosphere is it's delicate because from one end you want to know about ionosphere, you need technologies, you need measurements, but from the other side you want to protect those instruments, technology from the effect you want to see. So it's always nice to understand in which side of the balance you want to put. And the regular, irregular behaviors it's important to know because we need to understand what alter and how the ionospheric plasma is altered. And of course, the problem with the ionosphere is it's a complex environment with it's made by complex system in complex interaction among them, and you have to always take into account the coupling with the geospace forcing and the forcing from below. And I thank you for your attention.
Questions?
Yes, there's one.